Hello and welcome back to OpenGL training tutorials. This is the second tutorial in the series of OpenGL training tutorials. In the previous tutorial I showed you how to set up an OpenGL window using Glut. FreeGlut actually, I'm using FreeGlut in this version. FreeGlut is a free version of the Glut library, which stands for OpenGL Utility Toolkit, and that library is used to do things like create the window for rendering OpenGL. This takes away a lot of the boilerplate code that you'd have to write if you wanted to write the Windows window class and Windows proc procedure functions. Anyways, I'm going to continue today with rendering, various ways of rendering. In the previous tutorial, I showed you a very simple way of rendering primitives, and that was using immediate mode. I'm going to go into immediate mode in a little bit more detail in this tutorial, and I'm going to show you two other ways to render using OpenGL. Also, I should note that a lot of these rendering methods are deprecated in newer versions of OpenGL. As of OpenGL 3.0, these features have been deprecated and they have been removed in OpenGL 3.1. However, they're still available in a standard rendering context. So we're going to show, and the reason why I'm showing you this is because it's just a lot easier to get started if you're a beginner using these methods. And in a later tutorial, I'll show you a slightly more complex way of rendering, which is actually the correct way of rendering primitives and models and geometry. And that method is called using vertex buffer objects. But I'm not going to talk about vertex buffer objects in this tutorial. Today I'm just going to talk about the old ways that were provided by OpenGL. Okay, before I get started, I want to actually talk about a little bit of theory of OpenGL and how it works kind of under the hood. So OpenGL, if you don't already know, is basically a large state machine. It's not really a state machine because in the way that you think of like a Turing machine, but it basically works by enabling and disabling several states. So if we take a look at this method here, one of the states I'm already working with here is depth testing. Depth testing allows you to draw things in the correct order. So basically, if something appears behind an object already drawn, it basically will be discarded and that fragment won't be rendered to the screen. This allows us to draw things out of order, basically, so we don't have to arrange vertices in a strict depth ordering manually, but OpenGL will do this for us automatically. Another such state is, for example, call testing. We can enable call testing by calling GL enable, and we use the flag GL call face. So what call facing does is it will make sure that only front-facing polygons are rendered. So front-facing polygons, for example, are polygons that have a clockwise or counterclockwise order. In OpenGL, by default, the vertice order must be in counterclockwise, and I'll show you what that means in a second. And in fact, I'll show you what it looks like if you don't draw the vertices in the correct order. There's lots more states. For example, the color is a state. So you set the color in OpenGL by calling the GL color 3F. That's a state. The vertex is actually it is kind of a state, but it's a final state, which means that all the vertex attributes that has been specified previously to GL vertex 3F will be applied, and that vertex will be pushed out to the rendering pipeline to be drawn. So that states. The other thing I want to talk about are primitives. So OpenGL supports several different types of rendering primitives. One such primitive is the quad, which you always start your primitives with GL begin, GL quads, and after you're finished rendering, you always have to call GL end. This ends the begin state, so you always have one begin state and an end state, which basically finishes rendering quads. You can render as many quads as you want between the beginning and the end state, or any other primitive for that matter, but you always have to make sure that for every begin you have one end. And as far as I know, you can only have one begin. You cannot have another begin following that begin and an end followed by that end. You have to end the previous primitive and then start drawing the next one. There are several other primitives that OpenGL has available. here is a picture showing the different primitives that are available. You can just draw individual points, in which case no edges are connecting the lines. They'll just be points. There are also OpenGL states that allows you to specify how large the point should be when it's rendered. The GL lines primitive, which is basically lines between two vertices. So the point between, for example, 2 and 3 will not be connected, and 4 and 5 will not be connected. You can just draw a series of lines. If you wanted to connect the lines, obviously there's a primitive for that. There's a GL line strip, which allows you to draw a string of lines, or if you're trying to render Bezier curves or something like that for debug reasons, then you can use the GL line strip. The GL line loop will actually close the last loop, the last vertex, back to the beginning. So if you wanted to make sure that it remains closed, use GL line loop. Probably the most common is GL triangles and GL triangle strip. These ones allow you to draw disconnected triangles for GL triangles. So every third vertex will be connected, and then the next set will draw another triangle, and the next set will draw another triangle. And GL line strip, OpenGL allows you to just draw vertices in this way, and these edges will be added automatically. You don't actually have to specify that there should be a line here. It will be automatically made. The triangle fan allows you to draw closed surfaces like a circle, for example. This is a really good way to draw a circle. And what happens is that OpenGL will, you start the first vertex in the center, and then every vertex around is going to be closing the triangle. Again, OpenGL fills in these lines for you, so you just have to specify the first vertex, then the circle, and then it will automatically close to the last vertex. So if you wanted to draw a full circle, you have to start, you start at V1, and then you render from V2 to V3, 4, 5, 6, 7, 8, and then you have to redraw V2, otherwise the triangle will not be closed. Quads, this is also a very common method to draw, especially for particles or cubes or whatever, which I'm using for this demo. And that basically allows you to draw a closed box or a closed square by specifying the 4 points of the square. The quad strip is the same idea, but basically you start with V1 and V3, V4, V5, V6, and OpenGL will close these ones again. And a GL polygon also allows you to draw closed, it's basically a closed line loop, and OpenGL will automatically triangulate all the vertices to create a solid piece of geometry. You have to be careful though, because for polygons, and this is a good reason why this primitive is actually deprecated in the latest versions of OpenGL, but you have to be careful that all of your vertices are planar, which means that they all happen, or they're all falling within the same plane. If they're not planar, you'll get weird edges in your polygon surface. Okay, so those are the different primitives you can use to render in OpenGL, and now we'll discuss different methods of actually rendering to OpenGL. The first method I'll discuss is one that we've seen in the previous lecture, and that's immediate mode rendering. So in immediate mode rendering, you always have to begin your primitive with GL begin. Then you draw all your vertex attributes first, followed then by the vertices. And again, like I said, GL color 3F sets the color state of every vertex that will be drawn after that. This is also commonly called a vertex attribute, but this is the color vertex attribute. And vertices have many attributes. Another attribute could be normal, so every vertex can have a normal vector, which is perpendicular to the surface created by that vertice or set of vertices. It can also have texture coordinate attributes. So this is immediate mode, and we've shown already this in the previous lecture. So another way you can render vertices is using a technique called display list, basically. So a display list allows you to basically create a pre-compiled set of instructions. For example, you could say, I want to store these instructions in a compiled display list and redraw that display list later. So to work with display list, the first thing we want to do is we need to create the display list before we can use it, obviously. There's two ways you can create it. One is with compiling it first, or optionally you can also render it at the same time that your display list is created. Now, that's a convenient method. You can draw it at the same time as creating it. If your display list hasn't been created yet, you can actually render a primitive at the same time as creating a display list. Now, let's first talk about display lists. So, in order to use a display list, we first need to define a display list handle, or basically an ID. IDs in OpenGL are almost always GLU ints. So we'll create a GLU int for the display list, and we'll just call this the cube display list. And for sanity, we'll just initialize that to 0. And we also need a function that's capable of generating a display list, and this particular function will actually just generate the exact same cube as I generated here in immediate mode. Okay, so let's do that. So we'll have a function. This function actually will create the display list, so we'll give it a display list handle as a return, and we'll call this function cube display list. And one of the parameters we'll have is I want to determine the size of the cube. Now, the size of the cube, that's basically the width, the height, and the depth of the cube. So because the size of the cube is the width and the height and depth, and I want the display list, the cube, to be centered at the current point of origin, I need to actually divide that by 2. So size divided by 2.0f. So for example, if I specify that the cube should be exactly a unit cube, then each side from the cube will be half of that, because it'll be centered around the origin. So let's take a look. So we first have to generate a list, and this is really common in OpenGL, that you first have to create a display list or a texture or a vertex buffer object. You first create something. You have to create an address for it, basically, or a handle to it in OpenGL. So GL for display list, we can use gen lists, and the OpenGL wants to know how many lists I'm going to be generating. Well, in this case, I'm just going to be generating 1. And then we say we're now going to create a new list, and we're going to use the display list that I just created, and I'm going to say that I want this display list to be compiled, because I'm not actually creating a list that I want to have compile and run. I think there's a compile and execute. This will actually render the display list as you're creating it, but I don't want to do that. I just want to compile it. So then, to remind me to end the list, I'll just do this, gl end list. I don't really need the braces, but just to get this indentation to know that I'm within the display list. And I'm going to draw quads. In fact, I'm going to draw exactly the same set of quads that I rendered here. So for this simple example, I'm just going to copy these, copy that, and we'll put this into our display list. Okay. So you can render pretty much, well, almost anything in a display list and recall the display list later. So basically what this is doing, this is generating inside this ID, well, internally in OpenGL context, this ID now represents this entire render function. But now in order to render this, I only need to call one function. As you can imagine, this is a highly optimized method for rendering two display lists. And now we just return the display list that we've created. It's probably a good idea to also make sure that if our cube display list is not null, so it actually contains a proper ID, we have to delete always the lists. So cube display list, and we only have one. So this is a bit of a, it's kind of redundant, because as I'm exiting this function, the context will go out of scope, and the context will delete everything. But if you wanted to save memory or just for optimization, it's a good idea to delete things if you're not using them anymore. So in this case, I'm not using the display list, so I'll just delete it. Okay, so now in order to render this, we're going to have another render function. I've already created one, I think. I have one, display GL. I'm going to split this up into multiple calls so that I can render different things. So I'm going to create an enumeration for the render type, or render type. Scene 1, make that 0. And make this one 1. And I know that I'm going to be doing 3 in this demo, so I'll just go ahead and declare that in advance. Of course, this is redundant as well because enumerations are automatically incremented, and we don't really actually need to know what their IDs are. This is just good practice to initialize the first one to 0, because then you're guaranteed that the next one will be 1, then this one will be 2, and so on. Okay, so I'm going to refactor this one a bit. I'm going to refactor this into a switch statement, and I'm going to switch on, I need to create a variable. So let's also create a render type, current render type, or we'll just call it current scene, and we'll initialize this to render type scene 1. You might just want to call this scene number or something. That's up to you, of course. And when I process the G render type, if I am doing render type scene 1, then I'm going to render scene 1, which I don't yet have a function for that. Let's go forward declare that one. Render scene 1, 2, and 3. Oh, so now we have some forward declarations for those. Display. All right, and I might as well go ahead and define the other cases as well. 2, 2, and 3. Then that will be scene 2, and that will be scene 3. And in the default case, I'll just ignore it. I know I'm going to be I'm going to be handling all the cases anyways. So, all right, let's go back to the end, down to the end here, and we'll create these functions now. Render scene 1, and we'll make render scene 2 and 3. Too many. 2 and 3. So let's refactor this. Change this to make this scene 1. And since swap buffers, and in fact you could argue that the clear statement as well here, actually I'll do the clear out here as well. And for this demo, I'm pretty much always going to be switching to model view and loading identity, but I'll just leave it in the render function. Okay. So that should be it. For render scene 2, I'm going to use the display list instead. So in order to do that, we're going to do the matrix mode again, GL matrix mode, GL model view, make sure we're in the right model view matrix, and GL load identity. So basically load identity sets the model view matrix back to its initial state, which puts the camera directly in the center of the world, looking down the negative Z axis. Okay, so we also want to position the camera, so we'll translate the camera. Now this is a camera transformer. Actually, this is kind of a tricky thing. We're not moving the camera itself. What we're doing is we're moving the rest of the world away from the camera. So the camera is always positioned at the origin, no matter what. The view matrix is always in the center. So the first thing we have to do is we have to push our scene back so we can actually view it. And since we know that the camera is facing down the negative z-axis, in order to view our scene, we have to push it down the negative z-axis to get a good look of at our scene. And since I'm I'm a bit of a perfectionist here, let's make those all floating point values. And I also have a rotate parameter, so I might as well use it, and we'll rotate that in all three axes, just so it spins nicely on all three. I didn't do that here. Let's do that here as well, so we can actually get a nice rotation on that one. So now that we've set up our scene and we've rotated our origin, we can then just render our scene, and for that we just go call list and our cube display list. Now I haven't actually created it yet, so I'm going to go back into initGL function, initGL, initglut, or just we could even do it after we just initglut, but before the main loop, we're going to create a cube display list with cube display list, and we want a size of 2 units. Yeah, that should be good, I think. Yeah, in fact, that's actually a good point here. I'm using these cubes here are actually 2 units in size on each axis, because they go from 1 to -1, 1 to -1 on each axis. So it's actually 2 units. So I'll make this cube the same size. Okay, now actually that's pretty much it, except for I need something to tell my current render type to go to scene 2. So I'm going to do that in the keyboard function. So if we hit 1 on the keyboard, we'll go to current render type equals scene type, it's render type. I should just look at my IntelliSense. And when I switch to this one, I'm going to set the clear color. So that's why I know I'm in the scene 1. So I'll make this one black, 0.0, 0.0, 0.0, and 1.0. And when I'm in scene 2, I'll set the clear color to white. Then I know that I'm in the second scene. And we'll make the current render type equals scene 2. And we'll add another one for, if I hit 3 on the keyboard, then I'll render scene 3, but I haven't actually written it yet, but we'll make that gray. Or your favorite color, maybe cornflower blue or whatever, if you want to feel XNA-ish. Inside joke. We'll just put these in parentheses. I think the latest compiler appreciates that. Okay, so that's pretty much it. We've written these ones last time in the previous tutorial, if you don't remember. So now if I run, I should see a rotating cube. And if I hit, oh, here's this error I actually was telling you about. And render scene 2 is the same cube, also with the same error. So what's happening here exactly? Well, these faces are all being culled away, basically. They're being clipped because OpenGL doesn't see these as front-facing polygons. So in order to fix that, I have to change the rendering order. I can show you what happens if you don't enable cull testing here. I'll get rid of that, and we'll run again. And now you'll see that all the faces are showing up, but this is deceptive because you're not actually rendering these vertices, or possibly in the right order. So we have to be very careful that we wind every vertice that's visible, that the front-facing vertices follow this counterclockwise order. Now it's possible to change this to clockwise. You can have the vertices running in the clockwise order as well, but it's an OpenGL state and you can change that. But by default they should be clockwise. So I'm going to make sure that my vertices are all rendering clockwise, and the way I do that is I have to make sure that they're all being rendered correctly. Now, I know already that it was the violet face that wasn't rendering correctly, and in fact, I think there are two faces that are not rendering correctly. There's this one, the violet face, and also the orange face. The orange face, you could actually see the inside of it, which is not ideal. So both the orange face and the violet face are out of order. So I'm just going to take a second to explain winding order for a second. And to do that, I'm going to just show you this small scene I just created in Unity and applied this winding order texture to this cube. So here on this side of the cube, we see that vertex 0 starts in the bottom left corner and vertex 1 on the bottom right, and they continue in that way in a counterclockwise order. If the vertices are winding in this order as you're looking at them, then this will be considered the front face. If you reverse the order of the vertices when you render them to the graphics card, then they'll be considered the back face. The surface normal has nothing to do with the front or back facing vertices. Faces, only the winding order of the vertices. So if you're trying to visualize this on a piece of paper, for example, you draw a three-dimensional cube such as like this, and these vertices have to be wound in this order, and these vertices have to be wound in this order, and the top vertices in this order. But on the other side, they have to be wound the other way to be considered back faces when you're looking at them from this direction. So it might be a little bit hard to visualize, but maybe you want to just open a modeling package like this, for example, and put on a texture to kind of remind you which vertices should be placed where. So if you print this out, you might want to label these as V0, V1, V2, V3, V4, V5, V6, V7. So there's 8 unique vertices in total, ranging from V0 to V7. I've also made another mistake here. The display list ignores the size parameter. Of course, I don't want that, so I'm going to rewrite this function in the blink of an eye here so that I take the size parameter into account, and at the same time, I'll fix the problem. So I've now fixed the rendering order for both the display list here as well as for the immediate mode. And now if I re-render the view, we see that also the magenta face or the violet face and the orange face are now rendering on the correct order for both the immediate mode and the display list rendering mode. So now I've shown immediate mode and I've shown display lists. The final method I want to show in this video is a technique called vertex arrays. Vertex arrays are the most similar rendering technique to vertex buffer objects, except they don't use vertex buffer objects. They use only client-side memory. Now, client-side memory is basically memory that resides on the client computer. So for vertex arrays, the first thing we have to do is we have to define a buffer or an array that defines the unique vertices for our geometry, in this case, a cube again. For that, I'm going to use a special struct called the vertex position color struct, and I'm going to create the position and color for each one of the unique vertices. So this is an interleaved vertex buffer. So it's always position, color, position, color, position, color. Optionally, you can also create multiple buffers for each vertex attribute. So for example, if you had a position attribute, you could have one buffer just for position, you could have another buffer just for the color data, and you could have another buffer just for vertex normals, for example. However, we only have 8 unique vertices, but we need to tell OpenGL in what order those vertices should be rendered. So for that purpose, we're going to use the index buffer. And the index buffer is 9 times out of 10 an unsigned int array or an unsigned byte array of the vertices in the geometry, and in the order in which they should be sent to the GPU. So for this case, the front face is starting at vertex 0 and 1, 2, 3. So as you can see, the order of the vertices in this buffer has no significance. It's simply the order of the vertices in the index buffer. So you also have to be careful that the winding order of these vertices is correct for front and back faces. Okay, so we have an index buffer and a vertex buffer that we can use to render our geometry. And we're going to simply send those buffers to the OpenGL rendering pipeline, and we're going to do that in the third scene here. So to do that, again, we set up our view matrix basically, and now to tell OpenGL that we want to render using client-side arrays, we have to enable these client states using the function enable client state, and we're sending two attributes. We're sending a color, and we're sending the actual position itself, and the position is always vertex array. So we first have to enable these client states, and then we have to tell OpenGL where that memory is located. And we do that using the special color pointer, vertex pointer, and normal pointer special functions to map the attributes to client-side memory. So the parameters here, it takes the first one specifies the number of elements in this attribute that is being sent to the GPU, and the type of the attribute. In this case, the types are always a float, and the stride. The stride basically says how much memory in bytes do I have to skip from the first element to get to the next element. It's not how much memory is in between the elements, but how much memory from the first to the next one. So usually this is the size of our entire struct. So we'll want to step one entire struct length in order to get to the next attribute. Same thing for the vertex positions. That's a three-component vector of type float, and the stride of that vector is again position. Now we have to send the first element of that array, the pointer of the first element of that array. Now that we've mapped our pointers to the client states, we can tell OpenGL to render them using the GL draw elements function, and we want to specify that our elements are specified in terms of quads because there are 4 vertices each, and in total there's 24 indices in this buffer, and the type of the index buffer is of type unsigned int. Again, we could have probably just used bytes for this, but because we have less than 255 vertices, but I just always use unsigned ints. And then we specify the pointer to the index buffer, which is going to be used to draw the elements. And this actually sends all the vertices and all the colors in the correct order to the OpenGL pipeline. And we cannot forget to disable the client states when we're finished. If we forget to do this, it's very likely that somebody else trying to use a color state, but perhaps not the color state that they require is still being enabled, they'll end up getting your buffer data sent to the GPU in place of what they expect. And you can imagine that chaos ensues. So always remember to disable these client states if you've enabled them previously in this function. So now, after we've set up the vertex buffer and the index buffer and sent them to our GPU via the client states, we can rerun our application, and we see this is in immediate mode, this is using display lists, and this is using the client-side arrays. Now you'll see that the colors are blending across the vertices. Well, this is normal because we're only specifying 8 unique vertices, and the color of the vertice is always going to be the same. In the case of the immediate mode, we specify 24 vertices, and for the first 4, for example, we specify green, for the next 4 we specify red, and then for the next 4 we specify blue for every single vertice. But for this drawing mode, since these are shared vertices, we can only specify one color, even though this vertice is shared with 3 other vertices on each corner. So that's why it's blended. I did not enable smooth shading or anything similar to that. This is the default state. Actually, I could, if I really wanted to, I could force it to be flat. I'll just show you this. This is again another state. So we have cull face, and if we want them flat, I think it was GL shade model. GL shade model, GL flat, then we get the similar effect as in immediate mode on here. So the color of the face is determined by the last vertex drawn in this mode. So the last vertex in this case was violet, and the last vertex on this face was white, so that face becomes white. But by default, if we don't specify a shade model, OpenGL will render faces with smooth shading. That pretty much concludes this tutorial. In the next one, I'm going to be talking about vertex buffer objects and the OpenGL extensions, and I'm going to pretty much abandon this method of rendering for the remainder of any of the tutorials. This, of course, does have its purposes. For example, when you just want to draw, for example, a skybox, and you don't want to have to define geometry for it because basically it's just 8 vertices. Or if you just want to debug something and you don't want to have to create a vertex buffer object, if you just want to draw lines on the screen, this is perfect. For drawing complex meshes with millions of vertices, this is absolutely not acceptable. This might be good, but still you have to send this client buffer data every single frame to the graphics processor in order for it to be rendered. Display lists might be slightly better, but again, I'm not sure, in modern implementations, they may actually store the display list on the GPU, but it's not specified in the extension or in the specifications what or where the display list should be stored. So next time I'll show you how to use vertex buffer objects, and that will allow us to optimize our rendering. Thanks for watching.